We are now going to take a look at the student's t-distribution, and this is what we're going to use to construct a confidence interval for the mean when the sample size is small. Now that means that it's less than 30. Now we know from our just previous discussion that when sigma is known or n is greater than or equal to 30, so this is called a large sample. Sample size 30 or more is a large sample. So when if you know sigma or if you have a large sample, we can use the z-distribution to construct a confidence interval for the mean. Here's what we used. That formula should look familiar. You take x bar, you subtract the z value. Now the z value, that is a critical value, depends on your level of confidence, times sigma over square root of n. Now you have to know sigma in order to do this. And then same thing on the other side, but with a plus. In fact, we might just write it conveniently like this. X bar plus or minus your critical z value times sigma over the square root of n, where this part right here, that is the maximum error of your estimate. But now also, if you don't know, let's say this, but if sigma is unknown, right, so you don't know sigma, but if sigma is unknown, and if if n is greater than or equal to 30, then what you have is s is almost equal to sigma. So what you can do is replace sigma with s. So we're just saying that if you don't know sigma, but you have a large sample, s and sigma are almost the same value, so you might as well just go ahead and use s right there, and you'll get a good confidence interval. So the question is, what happens if both sigma is unknown and n is less than 30? So you don't know the standard deviation of the population, and you have a small sample. Well, if that's the case, what we do is now we use what's called the student's t-distribution. So let's take a look at that. So you may recall this, that when we did large samples, we had this. So recall that the z, the standard score was x bar minus mu divided by sigma over square root of n, right? That was how we standardized values. But now we don't know sigma, so we're going to replace it with s. But when we do that, we have to use a new distribution. So what we're going to have now is t is equal to x bar minus mu, but now it's going to be s over the square root of n. So for small samples, it may be that s is not even close to sigma. So if you use s instead of sigma, you can be making a big error when you make your computations. Let's write some characteristics of this t-distribution. So first of all, it's bell-shaped like the normal. Now, it is also a family of curves. Now, a family of curves means there's a collection of curves, like I've drawn some here. And the member of the family depends on the sample size. So for a small sample, like, it's hard to see all this, but maybe I'll try to do it like this as we go. If you have a small sample, like at n equals 4, you're going to have a bell-shaped, but it's going to have these kind of thick tails, and it does not come up very high. Oh, I missed it. Okay. So that's at n equals 4. Now, if you take a bigger sample, say like n equals 10, right? If you take n equals 10, then you might get, right, as the sample size gets bigger, you're still going to get that bell shape, but the tails become less thick, and it gets a little bit higher. That might be for 10. And then if you take a sample of size 20, then the tails get even less thick, and it gets higher. It's starting to look more and more like the normal curve. And in fact, we can say this, that as n increases, right over here, as the sample size increases toward 30, t approaches z. So in fact, I'm even going to say it this way here. As n approaches 30, the t-distribution approaches the z-distribution. And maybe you can see what happens. What happens when you hit 30, all right? And when you hit n equal 30, then you can use the z-distribution, right? When n is equal to 30, this curve here looks almost like this one. So at n equals 30, you can go ahead and use this. If n is less than 30, you can use this. And the mean, the median, and the mode are all in the same place, and they're all at 0. Right? So this is like z. We've already standardized things out. So the mean, median, mode, they're all there right at that point of symmetry. They're all equal to 0, just like in the z distribution. And just as the z-curve does, this t-curve never touches the horizontal axis. So like, okay, I'm going to put myself right here at the 0. Now, if you look at these tails, well, I didn't draw it too well, but they just keep going out, 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 and getting closer and closer to the horizontal axis, but they never touch it. So in this case, the t-axis is, the horizontal axis is called an asymptote. You may have heard that word before. And the last thing here, number 5, is that the area under the curve is 1, just like the z distribution. Now we need to talk about what is called the degrees of freedom. So here's what we mean by degrees of freedom. The degrees of freedom, df, all right, that's the number of free choices that you have after a sample statistic such as x bar is computed. I'll show you an example. Suppose we've got this small data set, 2, 4, 6, 8. All right, now find x bar. Okay, well, x bar is just this, right? X bar is equal to, add them up, 2 plus 4 plus 6 plus 8 over 4. All right, this gives us, what do we get here? 10 and 10, 20 over 4. X bar is equal to 5. All right, so that the mean here is 5. So here's what we might think of as a simple example. Suppose you've got 3 numbers, and you know that when you add them together, you get 10, right? So you've got something like this, right? You've got this number plus this number plus this number, and when you add them together, you get 10. Now, how many degrees of freedom do I have? That means how many of these 3 numbers am I free to assign? Well, I'm going to claim I have 2 degrees of freedom, because if I do this, what if I put a 4 here and a 5 here? Okay, I'm free to choose the 4, I'm free to choose the 5, anything I want, but what about this one here? Am I free to choose that number anymore? No, not at all. 4 plus 5, that has to be a 1. What if I chose this one to be a 2, this one to be a 2? Am I free now to choose this one? No, I'm not, because it has to be a number that when I add to 4, I get 10, right? So I have no choice for this one. This one has to be a 6. So the point is I'm free to choose two out of those 3. So in general, like here I have 3 numbers, I'm free to choose 2. So in general, what we're going to say is this: the degrees of freedom is equal to n minus 1, right? Like in this case, it's 3 minus 1. I can choose any 2, but the third one's determined. So degrees of freedom is just going to be your sample size minus 1. Let's do an example of trying to find a critical t-value. So suppose we want to find, we're going to use a table to find a critical value, call it t sub c, just like we did z sub c, for a 95% level of confidence with n equal 18, so sample size of 18. Here's a table of t-values. Now we have to figure out how to read this. So there's a lot going on here. So there's going to be several things here. We're going to be able to find confidence intervals, and then down here, this is for hypothesis testing. We're going to do this in the next chapter. So right now we're dealing with confidence intervals. So if you look over here, what we have is this. We have a one-tailed area, all right, that is for this right here. That's for hypothesis testing. We have a two-tailed area, that's this one down here, and that's for hypothesis testing. What we want is confidence level, all right? So we're going to be reading from this row right here. All right, so how you do this is just this now. Look for degrees of freedom. Now, for us, let's write it over here. Since n equals 18, degrees of freedom we know is n minus 1, so it's 18 minus 1, so it's equal to 17. So we have 17 degrees of freedom. So what we're going to do is we're going to look down degrees of freedom until we get to 17. It's right here. And now we just read over to the third the third row here, right? That's our confidence level. So, what did I say? 17. And over to the, okay, you have to look carefully here. I want the 0.95 column. There it is right there. So I get 0.95. Now I got to get this intersection here of 9,5 and 17. Okay, 9,5. I think that's it there. So I just magically made the table get bigger. So 17 degrees of freedom right here over to the 0.95 column. Is that it? Nope, that's the 9,8 column. There's the 9,5 column. Okay, straight edge might help here. All right, 17 degrees of freedom. I'm getting 2.110. So T, I'm getting at 95%. That critical value is going to be 2.110. And what it's giving us is under the T curve, right here's the T curve. Now it's kind of normal, right, but thicker tails. The high point is 0. Now the critical values going to be out here. It's going to be negative 2.110, positive 2.110. And what we're saying is that in this interval here, we have captured 95% of the area under that curve is between those two values. So how much area is on the outside, how much is here, and how much is over here? Well, if this is 95%, what's left over is 5%. So this is going to be 0.05 divided by 2, or 0.025, and same thing over here, 0.025. Now remember, they're positive numbers because we're dealing with the areas. The negative numbers are these right here. Those are on the horizontal axis. Let's do another one, just so we know how to do it. We're sure, confident. Okay, what's the critical value for a 99% level of confidence when we have a very small sample, say of just size 6? So degrees of freedom, we know is n minus 1, so we have 6 minus 1. So degrees of freedom, we have 5. Now look under the 5 degrees of freedom over here in the table. I'm over in the table, 5 degrees of freedom right here, and look over to the 99% column. Now remember, we don't use the top one yet. We don't use the bottom one. These are for hypothesis tests. We want the third row for confidence levels. So look under 5 degrees of freedom over to 0.99. Is that it? Yeah, 0.999. I want 990. Okay, so right there, if I follow it to 5, I'm getting 4.032. So the T value is 4.032. And the image that goes with this is, there's the T distribution. Oh boy, I didn't do very well on that one. There's a T distribution, kind of like it's just a drawing. Just draw a bell-shaped curve. The high point is 0. Now, if you come to the left, over here, to negative 4.032, and positive over here, the positive 4.032, in this interval right here, T, what's the probability that T is in this interval? That probability is measured by the area under the curve, and that we decided was 0.99, right? We've got 99% of the area under the curve. So how much is outside here? How much area is left over? Well, I think it's going to be 1%, and then if you take that 1% and divide it by 2, you get 0.005, right? So 0.5%, and 0.005 here. I think that's probably enough for one section, so we're just introducing the T distribution and seeing how to compute critical values. In the next section, we'll actually construct a confidence interval.